Have you ever wondered what a perfect, still circle has to do with the flowing, dynamic waves that are literally all around us? Well, it turns out, everything. We are about to pull back the curtain on one of the most beautiful secrets in all of mathematics, how a circle's simple code generates the rhythm of a wave. Let's get into it.
So yeah, this is the big question for today. I mean, it seems impossible, right? You've got this static, closed loop on one hand, and then this moving, repeating wave on the other. But stick with me, because by the end of this, you're going to see exactly how they're just two sides of the same incredible coin. Okay, first things first. We kind of have to upgrade our whole way of thinking about trigonometry. You know, most of us learned it in school as SOHCAHTOA, all about triangles, angles, and sides. And that's fine. But to really unlock its true power, the stuff used in calculus and physics, we need to think bigger. We need to apply it not just to angles, but to any real number you can think of.
So here it is, the big idea, the secret sauce. We're going to take any real number, let's just call it t, and we're going to imagine it as a distance we travel along the edge of a perfect circle that has a radius of 1. We call that the unit circle. This simple idea, this is the bridge that connects the abstract world of numbers to a geometric shape. And trust me, it unlocks everything.
So now that we're on the unit circle, we've got to set some ground rules. Think of this like learning the basic genetic code of the circle, the two fundamental instructions that are going to build everything else we talk about.
All right, our first instruction is cosine. It's super simple. After you've traveled your distance t along the circle's edge, you'll land on a specific point. The cosine of t is just the horizontal position of that point. It's x-coordinate. That's it. That's all it is. Cosine is x.
And you guessed it, our second rule is sine. It's the vertical position of that exact same point. It's y-coordinate. So from now on, you can think of any point on this unit circle as just being cos t, sine t. These two little rules, they are the entire foundation for everything that's coming.
And what's cool is that this table just shows what naturally happens when we follow those rules. As you journey around the circle, the signs just make sense. You know, in the first quadrant, you're up and to the right, so both x and y are positive. That means cosine and sine are positive. But then you cross over into the second quadrant. Now your x-coordinate is negative, right? So cosine becomes negative, while sine at the height is still positive. It follows the geometry perfectly.
All right, we have the rules, we've got the code, now for the grand reveal. This is the magic trick. We're going to take this spinning circular motion and we're going to literally unroll it, unleashing the gorgeous wave pattern that's been hiding inside the circle this whole time.
Here's exactly how we do it. Just picture this. Imagine that distance t that you travel around the circle is now the horizontal axis of a brand new graph. Now for every single point you stop at on the circle, you take its height, remember that's the sine value, and you plot that as the vertical value on your new graph. As you move around the circle, what happens? The height goes up to 1, back down through 0, all the way to -1, and then back up to 0. As you trace that path connecting all those dots, boom, you have just drawn a perfect sine wave.
This whole unrolling process proves something absolutely crucial about these functions. They are periodic. They repeat. Think about it. The distance all the way around a unit circle is exactly 2 pi. So once you've traveled that full distance, you are right back where you started. And that means the wave pattern you're drawing has to start repeating itself too. One full trip around the circle gives you one full cycle of the wave. It's that direct.
So we've got our basic wave. But let's be honest, the basic version can be a little boring. What if we want to change it? Well, now we get to become wave designers. Let's open up our toolkit and see how we can control the height and the width of these things.
The very first tool in our kit is all about controlling the vertical reach of the wave. It's called the amplitude. This is how we decide how high the peaks are and how low the valleys go.
And it's incredibly simple to use. All you do is multiply the entire function by a number. So let's say you multiply by 2. Bam! You've just stretched the entire wave vertically. The basic sine wave goes between +1 and -1. But y equals 2 sine x, that one stretches all the way from -2 up to 2. Its amplitude is now 2. Easy as that.
Okay, next up, our second tool is for controlling the horizontal shape of the wave. This one is called the period, and it's basically the length of one full cycle. We can use this to either stretch the wave out or squish it together.
Now to do this, we multiply the variable inside the function. So check out y equals sine 2x. What this does is it basically puts the wave on fast forward. It forces it to complete its whole up and down cycle twice as fast. So where the original wave took a distance of 2 pi to finish one cycle, this new, faster wave does it in just pi. We've compressed it.
Okay, last part. Let's look at the fundamental laws that govern this whole new world we've built. And don't think of these as boring formulas to memorize. No way. These are the laws of physics for circular functions. They explain how everything behaves and interacts. And the most important rule, the absolute king of all the rules, comes directly from where we started. Remember the equation for a unit circle? It's x squared plus y squared equals 1. Well, since we defined x to be cos t and y to be sin t, then it has to be true that cos squared t plus sin squared t equals 1. It's just a Pythagorean theorem, dressed up for a party on the unit circle.
And from that one fundamental rule, a whole universe of other powerful tools just appears. There are formulas that let you figure out the sine of two numbers added together, or the cosine of a doubled value, or even a halved value. It's like a complete Swiss Army knife for manipulating and understanding waves.
So there we have it. We've gone all the way from a simple point on a circle to a complete system for building and controlling waves. And that brings us to one final really exciting question. Now that we have this incredible toolkit, what parts of our world can we start to describe? From the sound waves that let us hear, to the light waves that let us see, to the alternating current that powers our homes, what can we now understand?